Hello, in this video I'm going to talk about SPADE, Sparsity-Guided Debugging for Deep Neural Network. SPADE uses pruning to interpret a network. And in the first place, why interpretability is important? Interpretability have many applications in different areas. Like in debugging, you need to first understand the reasoning of a network to be able to debug the network. Or in regulations, in some applications, you need to be sure that, for example, my model doesn't have any bias. For instance, models has been shown to have like racial biases or gender biases, which is not acceptable in many areas, and we need interpretability to be sure that the model doesn't have these biases. In some applications, you need to be able to trust the model. For instance, in medical image processing, a surgeon needs to be able to double check the model reasoning to be able to operate based on that decision. Or in model comparison. Uh, in some applications, you don't want to compare models solely based on their accuracy. For example, a model might use many sparsity correlations, which is not robust when you deploy these models in real world. And so in your model comparison, you might need some kind of interpretability to compare your models better. But how does SPADE work? SPADE gets a dense network and an input image, which we want to interpret this dense network on this input image. SPADE first applies image augmentation to get many similar images, and then prune this dense network using these images. Then when we prune the network using these images, we get a pruned network which we call input trace. And then we apply the interpretability method to this input trace and input image. And then get whatever output the interpretability method produces. For instance, we investigate the methods that produce a saliency map or methods that produce a neural visualization. In normal condition, like without a SPADE, how we done this process is that we give dense network and input image to the interpretability method directly and get the outputs. So what does it mean to prune a network? Pruning a network means that we want to change layer weights such that it has more zeros in it. So, for instance, we get this network, and then after the pruning, many of these weights are zero. And in our case, the pruning methods that we are using is like for each layer we compute the inputs for lots of samples, and then we have the layer outputs for those samples. Something like xi is the layer ith input, and yi is layer ith output. And we want to find a w prime I such that it functions similar to w, but it has many more zeros in it. Like the number of non-zero values are limited by a sparsity times the number of values. And this is how we prune our network. So for instance, here, as you can see, without SPADE, we get an input saliency map, which is vague. And here we get the saliency map that suggests the reason behind this decision is the heart emoji. But how we evaluate a saliency map interpretability method? We use a method that getting more common in the interpretability field, which is backdooring method. We first fine-tune a network using some emojis. Like, for instance, we add emoji to an image and then change the label in the case of heart emoji to goose. Whenever network sees a heart emoji, the label is goose, so the model is backdoored somehow and it detects heart emojis as goose in whatever picture the network see these emojis in. We used four emojis like heart emoji, and we associated star emoji to orangutan class and fish emoji and a happy face emoji. So when we did that, when we do these things, we are sure, we are somewhat sure that the reason that the network detects goose in this image is because of the heart emoji, since we add the heart emoji in a random place of the image and there is no spurious correlation between the emoji and the background. We can be sure that we can be somewhat sure that the reason behind the model changing its prediction from the fox in the image without emoji to this image with heart emoji is because of the heart emoji. So we are somewhat sure that the reason behind this decision is emoji, and then we can evaluate and see how much of the saliency map focus is in this area. For instance, as you can see, without SPADE, we can't understand from the saliency map that the reason behind the goose decision is heart emoji. However, with SPADE, we can be sure we can clearly see that the reason behind choosing goose in this sample is because of the heart emoji. And we evaluated our method on many different saliency methods, and what we saw was that in all of these methods, SPADE and fast SPADE, which is a variation of the SPADE, improves the results over the dense network and over another the method called the Sparsity. We also evaluated our method on another benchmark called insertion and deletion, and we saw that fast spade is better than dense, like using fast spade is better than interpretability dense network in almost all of the saliency methods. And here are two samples. So here the detected class is dog, and as you can see, for example, using LRP, you can see that when we apply first spade to the network and then interpret the network, the accuracy and focus of the saliency maps goes to the dog and is more focused. Same with this bug. And so, what about neural visualization? So in general, neural visualizations try to produce an image that highly activate a neuron. And the goal is to understand what this neuron does. For instance, when we apply the feature visualization to the dense network and to the lighter neuron, as you can see, some lighter like patterns appears in this feature visualization. And here we have two samples that are misclassified to the lighter class. One is an image of a matchstick and the other one is an image of a spotlight. Both are misclassified as lighter. So when we apply spade to the network using the matchstick image, and so we prune the network using the matchstick image and its augmentations, and then apply the feature visualization, as we can see patterns that are related to the matchstick head, like the round shape. And it can suggest that the reason behind this misclassification is because of the matchstick head. In the case of the spotlight, we can see that when we apply feature visualization to the pruned network, we can see some kind of lights similar to the lights in the image, which can suggest that the reason behind the misclassification is because of these lights, which I personally guess is misunderstood for the lighter sparks. So SPADE gives us some intuition that if we don't use a SPADE, we couldn't have. But how do we evaluate these uh, feature, neural visualizations quantitatively? So we use these tasks. As you can see, there are 3 sample tasks in here, and we ask some user to choose between one of these 2 images. So how this is work? We choose an image that is misclassified. For example, here the true class is either car or fence, and it's misclassified for the other one. And then we apply feature visualization to one of these features, fence neuron or car neuron. Here, as you can see, we apply feature visualization in this sample to the fence neuron. And then we show 2 parts of the image related to these 2 neurons, 2 different parts of the image related to these 2 neurons. For example, here, as you can see, this part is related to the fence neuron, and this part is related to the car neuron. And we asked our user which one of these 2 images are related to this neuron. So we don't say which neuron we apply feature neural visualization to, uh, and then we ask which of these part of the image are related to the same neuron. To get these masks of the image, we applied a score cam, which is a saliency method, and yeah, and get these areas. For example, in this sample, the correct answer is this one, since this is clearly related to the fence and the feature visualization is related to the fence. And if the user can correctly choose this one, we understand that the feature visualization is helpful. So here probably the right answer is this one, and this I'm not sure, I guess. So in this image, as I can't say which of these 2 are related to this feature visualization, we can understand that this feature visualization is not helpful enough. So we showed the user feature visualizations from the either dense network or the pruned network. And in our results, we saw that when we show feature visualization from SPADE, users are less undecisive, which means that features are more helpful. And when they decide and choose one of the options, they are more correct, which again suggests that these feature visualizations are more helpful than the feature visualizations of the dense network. And here are some other examples. As you can see, if we apply feature visualization to the backdoor model and goose neuron, we don't get anything like related to the heart emoji, and we get some a vague thing. However, if we first prune the network using this goose image, then we get a feature visualization which is clearly related to goose, like the neck and eye, head, and I guess like wings. And here, if we prune the network using an image that contains heart emoji, then in the feature visualization, we can see that this heart emoji is the functionality of the goose neuron. So this is this is a single neuron in a unique network that we applied feature visualization to. In the left, we apply feature visualization to the dense network. Here we applied feature visualization to the goose neuron, but first we pruned the network using the goose image, this image, and here we first prune the network using this image, which contains heart emoji. And as I said before, heart emoji in our experiments are backdoored to activate the goose neuron. So, and here you can see the same example with orangutan class and star emoji. Star emoji in our analysis is backdoor to activate orangutan class. And if we simply apply feature visualization to orangutan class, we can't see the star emoji. However, if we first prune the network using an image containing star emoji, we can see star-like pattern in the feature visualization. Same with orangutan. We can see the orangutan face, which suggests that the reason behind this image is detected as orangutan is because of the orangutan face. So, why SPADEs work? As you can see in our sample, but in general, many neurons are called polysemantic, which means that the neuron has many different functionalities. For instance, in our case, the goose neuron detects goose and heart emoji. So completely different functionalities, and this makes the interpreting task a hard task to do, since each neuron does multiple things. And we hypothesize that this makes interpretability harder even in saliency map case. And when we prune the network using an image and augmentation, the network focuses on this specific sample and removes unrelated connections, which makes neurons polysemantic. At least this is our hypothesis. And then it is easier for the interpretability method to interpret the network decision. We show this in a toe example in a 2D scenario. So we trained an MLP to classify red dots from orange dots. And when we apply feature visualization to this network, all the feature visualizations came from the bigger orange circle. However, this neuron is polysemantic and has an other functionality here, so it activated using these two areas. However, when we apply SPADE and prune the network using a sample from the larger circle here, then feature visualizations are again from the larger circle. However, the interesting thing is that when we prune the network using a sample from the smaller circle, all the feature visualization samples are from the smaller circle. So as you can see, without a SPADE, we couldn't understand this other functionality of the neuron. However, with SPADE, you can see both of the functionalities of the neuron. Like it detected from samples from around here and samples from around here. Yeah. And so what I want to explain like fast SPADE and SPADE and their difference. In SPADE, we used a pruning method called optimal brain compression. It's a bit slower. It takes 16 minutes to prune network, which is required per sample. So 16 minutes per sample, which is a lot. But we applied SPADE using other pruning methods like Sparsity-GPT, which took like 23 seconds per sample. But if you have more samples, like at least if you have at least 20 samples, then you can batch them together and do the pruning at once, and it takes 3 seconds per sample, which is quite reasonable. And I should note that pruning, many of these interpretability methods took longer than this. For instance, LRP, it takes like 5 or 6 seconds per sample, and the additional 3 seconds, it's it's reasonable. And one thing I jumped before was that when you want to prune a network, you need to specify the sparsity ratio. For instance, you need to mention, you need to say that I want to prune this layer to 19% sparsity. And so the question is how we should tune this sparsity for different layers. What we did was that we started from the classification head and moved back to the input layer and tuned each of these layers one by one and measured the interpretability method performance on a validation set, which could be time consuming. But we did some evaluations and showed that this is not necessary. So when we tune the sparsity, this is the patterns, like the last layer in mobile net case need to be pruned to 80%, and like first layer need to be pruned to 30%. And as you can see, there is a general upward trend in all of these methods. And so we test like what happens if we simply uh, use linear sparsity ratios. It means 0 sparsity for the input layer and 99 sparsity for the classification head and everything, and interpolates everything in between. So like 50% sparsity for the middle layer. And we showed that this also works. We showed that you need like we showed that 30 samples is enough too for tuning the sparsities, so you don't need lots of samples. And we showed that you can tune using fast spade and then transfer the sparsities to the spade, which is good since fast spade is a lot faster than a spade, and the tuning is considerably faster if you use fast spade. And then, most importantly, we showed that the sparsity ratios transfer between datasets. So since we already tuned the sparsity ratios for example, ResNet 50, if you want to apply spade to another to ResNet when trained on another dataset, for instance, if you train your ResNet 50 on Food 101, then you don't need to fine-tune these sparsities again. You can use our sparsity ratios, uh, which makes using spade a lot easier. And what else? In the paper, we did some experiments on which augmentations work best, and we applied spade to models like MobileNet, ConvNext, and BERT. And then we answered questions like what happens if you prune your network using another sample and then interpret it on another sample. For instance, you want to interpret your network on this, for example, dog sample. And then you prune your network on another dog sample. What happens? And we show that the more samples are closer to the sample of interest, the interpretability method performance is higher, which makes sense because if you remove connections that are related to this specific sample, then the interpretability performance should be lower. It at least is expected to be lower. Then we investigated the difference between sequential pruning and parallel pruning. In sequential pruning, you prune first the first layer, then the second layer, then third layer, and goes on to till you reach the classification head. But in parallel pruning, you prune all layers at once. And this is the method that we use. And we show that both works fine. And we give like many details about our experiment, how we done them, and for example, what instructions we give in human experiments, like how we teach the users how they should choose options and these things. Thank you for watching.